In this section, we're going to look at the law of sines and also the ambiguous case as it relates to law of sines. The law of sines here is a simple set of three ratios, a over the sine of a, b over the sine of b, and c over the sine of c. In using the law of sines, there is no requirement for a right angle. We can simply have information here we can cross, multiply, and solve. So a right triangle is not a necessity for a law of sines like it was previously to use our sine, cosine, and tangent to solve triangles. A couple of notes here. If we had just any kind of triangle, it doesn't matter what the shape is, angles are our uppercase letters. As a reminder, our sides or our lowercase letters are opposite their uppercase or their angles. So angle A or side A is opposite angle A, side B is opposite angle B, and side C is opposite angle C. Another side note here, depending on what math textbook you might be working in, you might see the law of sines written with Greek letters for the angles instead of uppercase letters. So here I have A over the sine of alpha, B over the sine of the Greek letter beta, and C over the sine of the Greek letter gamma. So depending on where you're working, you might have uppercase letters for your angles, you might have Greek letters for your angles, but both of those will designate the angle there. But once again, the law of sines does not require the use of a right triangle. We simply have to have one of our ratios filled out so we can cross multiply and solve for the rest of our information. A couple quick examples here. Solving our triangles, we're going to find all of our missing sides and angles. Angle A is 32 degrees, B is 81.8, and side A is 42.9. So I'm going to set that up, 42.9 for the sine of 32 degrees equals side B, which we don't know, or the sine of 81.8 degrees. And we don't know side C, nor do we know angle C. However, we can find angle C pretty easily because we all should know the angle sum of a triangle is 180 degrees. And I have two of my three other angles, so I would subtract those two angles from 180 degrees and we get angle C to be 66.2 degrees. From here, I'm going to go ahead and cross multiply with our first two ratios, which create a proportion here, and that will allow us to solve for side B. So side B times the sine of 32 degrees equals 42.9 times the sine of 81.8 degrees. Before I solve or plug my information in the calculator, I go ahead and divide by the sine of 32 degrees. That way I have B by itself. And if I go ahead and do that, I'll get side B to be about 80.13. I'll repeat the process for C. We found C to be 66.2 degrees, so I'll make that substitution. And I'm just going to use the first and the last ratio, so I'm going to cross multiply from here to here and from here to here. So side C times the sine of 32 degrees equals 42.9 times the sine of 66.2 degrees. And once again, we'll divide by the sine of 32 degrees. And if I divide by the sine of 32 degrees, side C is about 74.07. And we've solved for our triangle, our missing pieces of information. We'll go one more time here just to make sure we're clear. Solve our triangle. If C is 79 degrees and 18 minutes, side C is 39.81, and angle A is 32 degrees and 57 minutes. Don't know side A, but we know angle A is 32 degrees and 57 minutes. Don't know side B, don't know angle B. And we know side C is 39.81, and we know angle C is 79 degrees and 18 minutes. You can see we have one of our ratios filled out, which is pretty much a necessity in order to be able to solve for any missing variables. I'm going to start out by we'll find angle B first. 180 minus our 32 degrees and 57 minutes plus our 79 degrees and 18 minutes, or ultimately angle B is 67 degrees and 45 minutes. I would then move on to solving for side A by cross multiplying with these two sets of information. A times the sine of 79 degrees and 18 minutes equals 39.81 times the sine of 32 degrees and 57 minutes. And I'm going to get A by itself by dividing by the sine of 79 degrees and 18 minutes. Just as a reminder, when you type that into your calculator, you can type in 32 plus 57 divided by 60, or if you discovered the minutes and seconds or minutes function on your graphing calculator, you can use it as well. But if we solve for A here like we've done, we would get A to be 22.04. And one more time, we have to solve for side B. We found B to be 67 degrees and 45 minutes. I'm going to cross multiply with my final two ratios, and I'd have B times the sine of 79 degrees and 18 minutes equals 39.81 times the sine of 67 degrees and 45 minutes divided by the sine of 79 degrees and 18 minutes. And that would get us B to be about 37.50. Again, we've solved our right triangle by finding our three missing pieces of information. From here, we have something called the ambiguous case. The ambiguous case exists if we're given two sides of a triangle and one of the angles that are opposite one of those two sides. We have the ambiguous case. What we're essentially going to investigate is whether or not we have two triangles, but there's three scenarios that exist. We can have exactly one triangle, we can have the two triangles, or the information can be such that we don't have a triangle at all. And we're going to map this out into a step-by-step process. I'm just going to read through these fairly quickly. Solve for the first obvious angle. You saw in our last two problems when we set up our ratios, there's usually something that is obvious you can solve for right away by cross-multiplying. That will be our first step. Our second step is moving on to check for that second triangle. So we're going to take that angle that we just found and subtract it from 180. This would be the second angle in our second triangle if we had one. And that is determined by the next step. We would add that second angle to the original angle. If this sum is less than 180 degrees, there is a second triangle. If that sum is more than 180 degrees, there's not a second triangle. And once we've determined whether we have one, two, or no triangles, we solve for whatever is left. And so starting here, I'm going to go back here. The reason we subtract from 180 is the sine of 30, we all know, is 1/2 or 0.5. And if we type that into our calculator, such as the inverse sine of 0.5, our calculator will pull up just the 30-degree angle. But if you think about your unit circle for a second, the sine of 150 is also 1/2 or 0.5. Our calculator does not pull that up, but it is possible to have a 150-degree angle in our triangle, so we have to investigate whether or not that is a possibility. And one more side note here with our triangle, just to give you an illustration, let's say I had this side is, let's say 15 units long. And let's say we know the angle right here is 20 degrees. Okay, we could have a triangle created by a side length of, say, 20 over here, and just find this remaining side. We could take that same information, we could go 15 here, we could go an angle of 20 degrees here, and we could bring this side, maybe this length coming back is 20. So we could have two different triangles created from the same set of information, which is essentially what we're saying down here with our ambiguous case. The bottom line is we have to investigate anytime we have two sides and one angle using the law of sines. So here's what that's going to look like. Number one, angle B is 55 degrees and 40 minutes. Side B is 8.94 and side A is 25.1. Noting right off the bat we have two sides and one angle, we're going to have to investigate the ambiguous case. 25.1 over the sine of angle A, 8.94 over the sine of angle B. Oops, we know angle B. Angle B is 55 degrees and 40 minutes. Now, C we don't know, and we don't know angle C either. So as I mentioned in our step-by-step process, the first step is to solve for our first obvious angle. You can see by setting up our law of sines, there's only one item I can solve for here, and that is the sine of angle A. So I'm going to take 8.94 times the sine of angle A, 25.1 times the sine of 55 degrees and 40 minutes. I'm going to go one more step and divide by 8.94. That way I'm solving for the sine of angle A. My record. Dang it. Okay, hopefully there's not too big a gap in there. And a little mishap here while I tried to open up the calculator. But we're working on our ambiguous case here. So I was going to pull up the calculator to show how this transpires. Over here on the calculator, I'm going to type in that expression. I have 25.1 times the sine of 55 plus 40 divided by 60. And I'm dividing that by 8.94. So I wind up with sine equaling re-enter that. So let's go back up here and enter that again now in degree mode, and I get sine equals 2.3184. Now if you think back to what we worked on back in chapters 2 and 3, we talked about the range of values here. Range of values for sine falls between -1 and +1. 2.3184, and I'll just illustrate it here. We would use our inverse sine to convert that to an angle, so second sine of that value, we're going to get an error message. Well, an error message is justified here because our sine has to fall between -1 and +1. 2.3 is well above that, so in this case, there is no triangle that exists. So there's our first example that says no triangle exists based on our ambiguous case. We'll start all over again, solve our triangle. If A is 55.3, side A is 22.8, and side B is 24.9. Noting right off the bat we have two sides and one angle. I'm going to set up my law of sines, 22.8 over the sine of 55.3, 24.9 over the sine of 55 of B, and we don't know side C, nor do we know angle C. So as we mentioned the step-by-step process, there's only one item we can solve for right now, the first obvious angle, which is sine of angle B. 22.8 times the sine of angle B equals 24.9 times the sine of 55.3. I'm going to divide by 22.8. And we'll show that as well. So I have 24.9 times the sine of 55.3 divided by 22.8. So our sine would be 0.8978. I use the inverse to convert that ratio to an angle. So second sign of that answer, and our angle is about 83.9 degrees. We go to the nearest tenth because we're the nearest tenth right here. So angle B was, I already forgot, 63.9 degrees. 63.9 degrees. Now my suggestion from here would be set up a little T-chart to check for a second triangle. Triangle number 1 and triangle number 2. Regardless of whether they have one or two triangles, angle A is given to us. It's not going to change. Angle A or angle A prime is going to be 55.3 degrees. We just solved for angle B in our first triangle to be 63.9 degrees. If we had angle B in a second triangle, angle B would be 180 minus 63.9 degrees. And 180 minus 63.9 would get me angle B to be 116.1 degrees. Now if you look at our second triangle, we have an angle of 55.3, an angle of 116.1. If we add those together, we get 171.4, which is not over our required sum of 180 yet, so we do have room for a third angle, or a second triangle in this case, and 180 minus those two angles be angle C of 8.6 degrees. Back over here, angle C is 180 minus these two, so 55.3 and 63.9 subtracted from 180 gets us 60.8 degrees. And then we plug each of those angles in. I'll show the second triangle first, 8.6 degrees here. So we cross multiply with the first and the last, and I would have C times the sine of 55.3 equals 22.8 times the sine of 8.6. I'd solve for that side, and side C would be about 4.1. And then I would repeat the process. I get rid of this 8.6 and use the 60.8 degrees and cross multiply again. C times the sine of 55.3 equals 22.8 times the sine of 60.8 degrees. And we'd solve for side C in that case, and side C would be about 24.2. So you can see an example. We have two triangles that would exist from our ambiguous case here. Let's try again here. Solve triangle ABC if A is 43.5, side A is 10.7, and side C is 7.2. So I started setting up my law of sines. 10.7 over sine of 43.5. We don't know angle B or side B, but we know side C is 7.2, and angle C is what we're going to look for. Once again, noting we have two sides and one angle. Anytime we have that, we have the possibility of the ambiguous case. We'll start out cross multiplying. The only thing I can solve for right now is C. 10.7 times the sine of C equals 7.2 times the sine of 43.5. Let's try that so we don't transpose it again. Sine of 43.5. I divide by 10.7. We have to convert that to an angle, and angle C would be about 27.6 degrees. From here, I'm going to do the same T-chart to test our idea of two triangles, first and second. Angle A was given information, so it doesn't matter whether they have 1, 2, or 16 triangles. Angle A is not going to change, 43.5. We just found angle C for one triangle be 27.6. So for our second triangle, angle C would be 180 minus 27.6, or it would equal 152.4 degrees. So right away, in a second triangle, we already have an angle of 43.5. We said our second angle would be 152.4. If we add those together, we have 195 plus degrees. Well, we can't have a triangle that has 195 degrees in it. So in this case, there is not a second triangle, and we just go back here and solve our first triangle for side B, and angle B I'm just going to plug those in very quickly. Angle A or angle B would be 108 degrees and 9 minutes. When I add these two together, subtract from 180, and side B would be about 14.7. So you see an example with one triangle, with two triangles, and with no triangles as we move forward here. So let's take a look at our next example here. Without using the law of sines, explain why angle A is 104 degrees, side A is 26.8, and side B is 31.3 cannot be a valid triangle. So I am going to go ahead and set up the law of sines even though it says not to use it. 26.8, or the sine of 104, 31.3, or the sine of B, and I'll just go ahead and tack C here on the end of it anyway. But if you look at this, our angles are opposite our sides, as you can see, but as we progress up, the size of the side, for example, the smallest side should be across from the smallest angle, the largest side across from the largest angle, and so on. So in this case, 26.8 is opposite to 104 degrees, which means angle B would have to be larger than 104 degrees. So even if I made 105 degrees, that's 209 degrees. I don't have room for a third angle, so I can't have an angle larger than 104 across from 31.3. So there is no triangle here because of the angles and the sides not being in the same ratio. All right, so one more time here with our ambiguous case, find the remaining parts. Let's just go ahead and set this up very quickly. Side A is 5.0. Angle A is 27 degrees. We don't know side B or angle B, but we do know side C is 9.0, and we don't know angle C. Once again, pointing out we have two sides and one angle, so we have the ambiguous case. We have to check for our second triangle. Solve for our first obvious angle. 9 times the sine of 27 equals 5 times the sine of C. Divide by 5, and angle C is going to be about 55 degrees. We'll make life simple and go the nearest whole degree since our angle up here. Once we have that first angle, that's when I suggest we set up the T-chart here. Our first triangle and our second triangle. Angle A, given information, does not change from one triangle to another. So A or A prime is 27 degrees. We just found side angle C here to be 55 degrees. If we have a second triangle, angle C is 180 minus 55, or in this case, 125 degrees. So if you notice, 27 and 125 add to be 152. So we have room for a third angle, and that angle would be 28 degrees. We could go ahead and put that 28 degrees over here, cross multiply with our first two ratios to solve for side B. B times the sine of 27 equals 5 times the sine of 28. And if we divide it by the sine of 27, we'd find side B, and side B would be about 5.2. I would then start back over again. In my first triangle, I have 27 and 55 degrees. 180 minus those two would get us angle B to be about 98 degrees. And we plug 98 degrees back in over here, and I'd have B times the sine of 27 equals 5 times the sine of 98. And we'd solve for side B in this first triangle and get about 10.9. So you can see a second time when we had two triangles, all based around this idea of supplementary angles, and our angle sum being 180 degrees. And that is our ambiguous case for the law of sines.